welcome everybody for coming to this conference. And it is a perfect weather for doing science. So you won't be distracted by sun or anything around. This is, I was prompted to think about this conference because we have established our company 15 years ago, but I won't be talking about that at all. It was a traumatic experience for me, and I would rather focus on something else. Those are nonlinear phenomena. There is this notion that science progressed so far that there is really hard to do any additional useful work. And in order to contribute to that science, you need to spend many years learning what has been done so far. And the thing is that even when you devote your time to doing just that, it is very hard to understand what's in the publication, in the past publications, simply because there is very diverse field. You can do photovoltaics, electrochemistry, solid-state physics, semiconductors, and in those fields they use slightly different languages, slightly different conventions, but most of all, they use the same names to describe different things. And when you are young practitioner in chemistry or in physics, you have really hard time to get to the bottom of things. And this conference is just one single attempt to show some basic stuff that may be useful in your day-to-day work. So most of the presentations will be deductive. And the name for the talk, not for the conference, is that great realization that we had that, okay, we build instruments for you guys, and we are supposed to know how they work, and we usually do. We have some knowledge on their doings, and they do measure what we think they do. However, when we are asked to interpret data from users of those instruments, it's very hard. Simply because there are still battles going on since 18th century that are perhaps quiet these days, but they are still unresolved, and people are confused about very basic notions in electrochemistry and electrovoltaics, photovoltaics in particular. And one of the realization is that if you look at presentations or application notes for instruments, you see that manufacturers tend to impose on you some presumptions that do not need to be satisfied in your day-to-day work. And one of the greatest one is a presumption that your system is linear. So this is why we'll be talking about nonlinear phenomena in samples, and I hope that it will be close to your heart after the conference, and you will see that there is, first of all, some simplicity involved and beauty as well, because not only it can progress your research, but you will understand your samples better, so you'll be better prepared to design sensors or better to design catalytic materials, things like that. So the first talk is devoted to the nonlinear phenomena, but first, it doesn't work that way. Yep, it works. Sorry. Let's see what linear phenomena are. You can consider for now an abstract notion of a system that has just an input and output. Thank you. Thank you. We are well prepared. So usually you have some control parameters that we provide with our instruments. Though we will see what those are, but the most abstract level is that you have some input to your sample and then you read out some parameters from it. And when the sample would be considered linear, it is when you have some input, it can be spread in time, and you get an output. If you have different input, you get different output, usually. If they were the same and those were different, this would not be a linear sample, okay? And now, you add those two inputs together, and the sample will give you also superpositions of the previous outputs. So this is the essence of linear systems. They preserve superposition. So this is I call this superposition because it is sum of outputs and this is a sum of inputs. Okay, and you also have scaling. If you have, you can multiply the input by some scalar, by some number. It will be either greater or lower. You expect the same to happen to the output. So this is for linear systems. And I keep missing this button. All right. Now, there is another class of samples. They are called time invariant. And most of chemists will know what I mean, because now when you have one input applied to your sample, you read out some output. Then you apply another input, you have different output. But when you go back and apply the first one, you again recover the same output. So your sample doesn't change in time, or it does not have memory. So it reacts as a blank sample every time, tabula rasa. After each experiment, you recover the initial conditions. And why I'm talking about that, it will be obvious in a moment. But now I will show some examples of those linear and time invariant systems. So this is the first one, the resistor. Second one, capacitor. And believe it or not, inductor is also a linear system. And now, you may have recognized those resistors, capacitors, and inductors, or even other things that are being presented to you when you do either impedance spectroscopy or electrochemical impedance spectroscopy. Those are elements that the equivalent circuits are built of. What I mean is that when you have a sample and you try to figure out its inner workings, you are being helped by the software and that will combine those linear elements and in order to see what capacitance in the sample is or what resistance and things like that. And the thing is that in the case of electrochemistry, certainly, and in other fields, those equivalent circuits are useless. Not only useless, they are confusing. They will direct you into the wrong path if you want to understand your samples. And but let's see why the linear systems are so nice that we try to shove them everywhere we can and use the theory for them. And so many instruments assume that your sample belongs to this category of LTI, linear and time invariant. And those systems are really simple. Why? Why is that? If you have a system in that category, you can provide it with input like this impulse at a given time, and you get an impulse response from the system. Okay, and this is, it started at, it was at T1 here, and now at T1 the system starts responding to this, and this is the response. In later times, the system will feel this this impulse, this original impulse, and all the information about the system is contained in that impulse response curve. There's nothing more to learn. If you know that that quantity, you know everything about your system. So you don't even have to do any experiments. You can calculate what the response of the system will be. All right. How it is done? You can have a general input function. This is this black curve here. You just divide it into pulses. Their height corresponds to the values of this function. It can be positive, negative, doesn't matter. And you just plot here the pulse responses proportional to the pulses you have divided your your input to. And you will add up all those pulses and you'll get the response. You can have a different look at the at this problem, and here it is. You can think about the response and the time at time 1 and wonder which part of input affects this value at time t1. And obviously, if you have this input at t1, it will just start rising, okay? So it will have all past, all future points of this input do not affect this value, because we have some causality here, and future events do not influence the current ones, okay? So this is why you have this pulse function reversed in time, because the previous values of x can influence point at t1, but future values cannot. And this is actually all written in this nice form. It is often perhaps difficult to understand, but when you read in textbooks, but here is the essence of the convolution. This is called convolution, and in the time space it looks like the integral. So this is the time reversed pulse function times input, and you will get your output at time t1. In general, you can drop the integral limits. You can go to infinity here, because this function is 0 for all future times. So it is, and linear systems are reduced to that equation here. If you know your input, or the input you would desire to apply to the system, then this impulse response multiplied by the input gives you the output. So you don't have to even buy an instrument. You can do it on your computer or on paper. And there is one more thing that I would like to convey here. I've been discussing time domain, but sometimes we go to frequency domain. And in dealing with input and outputs, you may have heard about Fourier transforms or Laplace transforms. They help you to just change the space that you are working in. Instead of dealing with time, you do this with frequencies. And if you do that for linear system, you have a corresponding quantity there. This is this transfer function. So the pulse, the impulse response is transferred to transfer function. And I'm mentioning this only because when you read application notes, papers, and you see that people are using transfer function, that means that it is most likely not applicable to your case, that they are dealing with linear systems. And it is tacitly assumed, at least, that those are linear systems, not nonlinear. All right. But, okay, we've been looking for linear systems, but what are those nonlinear, okay? Because even if you are trained in physics, in math, or other fields, there is a plethora of phenomena that can be described as nonlinear. And in order to make your mind, you need to know what we mean by nonlinear. So here we will be breaking the assumptions or the conditions for a system to be linear. First condition to break is that we break this superposition rule. If you have two different inputs, can be the same, doesn't matter, and you have two different outputs provided by a system, then when you combine them together, the inputs, you won't get a combination of the outputs. You will usually get something else as well. And the scaling also doesn't work. You can apply more of the input and you won't be getting the same scaling of the output. If it wasn't enough, also time invariance is broken. Time invariance, it has nothing to do with special or general relativity. It is really called time invariant and time variant systems. So now the situation has changed because your system tends to remember its history, meaning that you do experiments in a given condition today on the sample. You repeat those conditions the next day, and the sample will give different answers. And in our practice, especially in electrochemistry, this is so familiar that results are hardly reproducible from day to day. And this is because those systems remember their past. So, if you are like most mortals, your samples do not belong to the LTI group. They belong to this NLTV category, which is nonlinear time variant. And it would be nice if you had tools to explore this type of samples, not just assume they were linear. Okay, but we will be focusing on electrochemistry and photovoltaics. So what kind of inputs will go down from this abstract level to more concrete? What are those inputs and what are those outputs that we can apply and measure? And The inputs typically are electric voltage that you apply to your sample. You can have some electric current applied. You can have light shining at your sample. You can increase temperature. You can have some charge there. There are those type of quantities that will be concerned. And those same quantities could be measured. So outputs are basically the same. I have put letters here because we'll be using them throughout those presentations, and also this is how they are used in our software for our instruments. And all right, then let's see how those nonlinear systems can be distinguished from linear systems. First, I will talking about this pair of voltage and current, right? Other quantities, I could have chosen, for example, voltage and light intensity. We are Fotonowy, meaning Photon Institute, so this is close to our hearts. However, this is the easiest to do. You just do IV characteristics of your sample, and you can see whether it is linear or not, because if you if you try to measure the IV characteristic for a resistor, it will look most likely pretty linear. Of course, there can be deviations at large values, but still this device is either linear or approximately linear. And I had a quarrel for some time with one of our friends that, come on, you can always find something that is nonlinear about even simple systems like a resistor. You'll see later that it is not correct, that there are some systems that are fundamentally nonlinear and they cannot be approximated by any linear system. So, example from photovoltaics. It is a PN junction. This one, I mean, the system, you have N semiconductor and P semiconductor, and they are in contact. There is some depletion layer formed in the middle. And for you who have experience with impedance spectroscopy, I dare you to explain the behavior of such a junction, very well understood, as we think about it that way at least, in terms of linear systems. There's no way. No way you can, no matter how many linear equivalent circuits you would provide, you won't be able to grasp the inner workings of this junction. In electrochemistry, this is practically everything. I still wait for an example of a sample that is both linear and time invariant. We have many friends around the world, and I ask them whenever I have a chance whether they can provide me with such an example. So far, no luck. And all right, so if it is that easy test to do to find out whether the sample is nonlinear or linear, let's look at those nonlinear samples. And so this is a characteristic of a diode, again PN junction. It is an exponent. This is why it is hard to really approximate it with line, because wherever you try to do this, the line will be different. And so you can say, okay, at this point of voltage applied, I will have some conductance here, and I can have a line here that will be tangent to this curve. Well, of course, you can turn your blind eye on the nonlinearity of this curve in some instances, but still you won't be any closer to understanding a sample. So what we do to show what nonlinearity means in the case of IV characteristic, and it will be true for any characteristic that you can think of, it is we can do Taylor expansion around that point. So we, for this particular voltage, we do Taylor expansion of this curve. Value of, we try to find out what would be the value of the current if we are around that point. And this is how we do this. So we try to have a small disturbance here. Small or large, it won't matter at the end, but we are around point V0. So when you do the Taylor expansion, you get terms like this. So this is the value of the function at that point. That's fine. Then you will have term that is linear in the perturbation. And this is the term. It has some coefficient. We don't care now what this coefficient is. Then you will have terms that are higher powers, second power, third, and so on. And you can have all of them. And we consider system linear if all the higher powers, I mean those coefficients from A2 to infinity are 0. So only at most A1 is non-zero. Okay? Then the system is linear, but it is usually not the case. And since we know that the simple, like a high school level mathematics applied to our IV curve gives us the feeling for the nonlinearity of the system, we can explore some nonlinear phenomena. And now I will have the input in this form. I will have voltage multiplied by some plane wave. I mean, this means that this voltage will change with some frequency. This is all there is. It is impossible to do in real life because you cannot apply just single frequency, this complex function. You need to apply also this with conjunction with the minus I omega t function. Like cosine, sine functions, they consist of two frequencies, not one frequency, plus and minus the frequency. But still, for simplicity, I just consider one frequency because it doesn't change the outcome and the conclusions. So when we do this, we see that we'll have this current calculated around that for this perturbation. We'll have term linear. This is the same as this perturbation here. We'll have terms squared. So this is the square. But here, the interesting part happens. You have this 2 omega, meaning that from one frequency, we got the original one, all right, but we doubled the frequency in our output, meaning that we can look for higher harmonics. Harmonics are those integer multiplies of the base frequency of omega. Now, there are some, in order to avoid those higher frequencies, you have this recommendation that if you use your perturbation in, for example, impedance spectroscopy, please keep this delta V small, so you won't get any harmonics in your output. Okay, but it doesn't make your system linear. It is as nonlinear as it was, because you change this V0 to something else and you can get completely different result. And more than this, you throw away useful information about the inner mechanics of your system. So another little more involved example of nonlinear effect. Now we have intermodulation. So this is really that simple. Instead of having one frequency as before, we will have two different frequencies. If we apply that, we'll have different terms. They are not important. They will be linear terms. This is zero term, I of V0. But also there will be this second harmonic terms and higher harmonics. And how do they look like? See, you just put the square over here, and you'll see what you will get. You'll have double the first frequency, double the second frequency, and their sum in the middle. It is even worse, because as I told you, you cannot apply just this single frequency like that. You have to add to it also its complex conjugate. You only can apply the real voltage to your sample. You cannot apply, I mean, at least I don't know how, and nobody else has figured out in real life, because you can do it on the paper, on your computer. You can operate complex numbers. But when you have a real sample and you want to apply the voltage, it is always real. So it cannot be counted. This is why you have to get rid somehow of this imaginary part. So you won't be able to apply just two frequencies. You'll be applying at least 4 frequencies, because there will be also a negative omega A and negative omega B. And you will get as a result not just pluses here, but there will be minuses. And higher harmonics will show you any combination of those frequencies. They can be 2 omega A plus omega B and so on. Minus, everything will be there. So you'll have, your nonlinear system will produce for you a plethora of frequencies that you have not applied to it at all. Still, it doesn't have to be a bad thing for you. You can use it to your advantage, especially, I mean, it is used in physics, in four-wave mixing, that for some reasons, the output may prevent you from seeing the original frequencies, omega A and omega B. For example, because they do not propagate through the system, through the electrolyte, things like that. But you can still find this intermodulated or mixed frequency that gets out. And you can look only just at this frequency to see if some phenomena happens or not. Okay, so you can engineer your experiments in order to employ this phenomenon rather than to try to avoid it at all costs. Well, by the way, you can ask questions. Don't worry about the time, because we have plenty of time, and this is those talks will be published for free on YouTube or some other platform. So you don't have to note everything. You can, if you have any concerns, please, you can raise them with me. The last nonlinear phenomena that I will be talking today is the rectifying effect. Again, this is the level of science we are doing here, but simple doesn't mean stupid, and this is certainly not. It took me many years to figure it out that it is that simple. So, anyway, you can have our perturbation. Now there is no constant term. I mean, just this perturbation. So if I go back to the to our characteristic, we are around that point, the 0 point, okay, for simplicity. So what we are doing, we are having our perturbation on the plus side of 0, small perturbation like this, and we get the current. Here is the current, so there is no 0 term because we are non-zero. There is first this linear term, quadratic, quartic, and so on. Yeah, cubic and quartic. Then you apply the perturbation on the other side of the 0. And you find the current that it presents to you. Again, it's almost the same. But for odd powers, we'll have minuses. And let's try to add those two currents. You can see that only even powers survive that addition. And what is this? When you add those two currents and you divide it by the perturbation, you will get a conductance. Okay? You will get a conductance. And if it is non-zero, that means that your sample conducts more in one direction than in the other. And this is the rectifying effect. Your resistance will depend on the direction of the voltage you apply to the sample, which is perhaps for some of you it is intuitive, but not for me certainly. You have just this stick, right? You apply voltage in one direction, it gives you one current, the same voltage in the opposite direction, different current. And still it is a rule in your samples rather than an exception. And all right, we had after a long time of thinking about those problems, I have come up with the idea that in order to understand anything from your in electrochemistry or in photovoltaics, you need to understand how photodiode does work. And believe me, it is not a simple thing. As you will see soon in the next lecture, if you look for textbooks, most likely you will be, you can come up here. There are 3 seats over here. Don't worry. Yeah. Oh, please join us here. All right. You have a strong group from Warsaw coming. Okay. And so, if you want to start in the nonlinear phenomena, you should understand a diode and then a photodiode. Then, what I also found useful is this Landauer's picture of transport phenomena. And this will be also talked today by Professor Byczuk. It seems like whenever you try to understand the samples in, for example, in electrochemistry, you are always faced with either difficult math or plethora of phenomena that are concealing from you the truth about the sample. And the power of the Landauer's picture is that is kind of, perhaps I shouldn't say that, but it is a TikTok version of physics. It gives you, in simple terms, it gives you a pretty good understanding of what's going on with your sample. And for some reasons, this author is still not that popular in academia. Of course, if you deal with mesoscopic or nanoscopic systems, you cannot escape the works by Landauer, because their current is ruled by different set of rules than we are taught in schools. Moreover, the set of rules devised by that gentleman also works in macro world. So that means that you can understand even macroscopic systems in that picture. And here is, for me, the most beautiful formula of all in that picture. It tells why the current flows at all in materials. And why is it? This is the current, E means this is for electrons, because it is useful to consider electrons, because those are the agents that are moving. I don't know if you will get more closure with that formula during professor's talk here, but I will mention it nonetheless. Sorry, we are there. You can have, so this is my system, and I will try to apply voltage to it. And this system on that end has one Fermi function, and on that end has another Fermi function. And when I apply voltage to it, one will go up. They are in contact, in electrical contact. One will go up, the other will go down. And you see, the current is given by this integral, by this difference first, and then the density of states. This you can forget for now. So it gives you all the asymmetries, all the thermoelectric effects, if you apply it carefully. And it is not rocket science. It is, you have just to compare the two Fermi functions that are easy to compare. All right. And perhaps you would like to get richer by the end of the conference. We'll have, we have announced it a couple of months ago that we are still looking for a good reason to save band bending. There are many phenomena found in literature that are explained with the help of band bending. And it was the greatest obstacle I had in understanding those explanations. Because it was, for me, it was replacing one mystery with another. Though I'm pretty fluent in quantum mechanics, still couldn't understand what was going on. And it turns out, as I'm convinced right now, that this band bending is a fallacy. You should never use this to explain anything, because it does you this disservice. You may think that you explained something, but it is not there. It simply doesn't exist. And perhaps you can convince us otherwise, that there is a good reason for having band bending. If you want to see the announcement and the price description, it is $1,000. Just go to the first post on our forum, and it is all described there. And it is easy money if you are convinced you understand that. So thank you very much. This is just in time, right? All right. We will now be switching to another talk, and hopefully you will enjoy talk by Professor Alicki, who will show his work on photodiodes, and it is not as you may have learned from textbooks. Then you'll be hearing from Professor Maciek about band gaps and what to do and not to do with them. And then there will be, I believe, Professor Byczuk on the talking about this Landauer's picture that I highly recommend, because it is beauty in its own. And then we'll have Dr. Bienkowski talking about hassles with electrochemistry and electrochemical cells. So thank you very much, and I will pass the mic to Professor Alicki.